Passt. Recht herzlich grüß Gott von unserer Seite von der OEGSL zum 5. Schneeseminar dieser Wintersaison. Diesmal hybrid, live aus der Axamelizum vom Lawinenkommissionskurs und über unseren Zoom-Kanal und über YouTube auch herzliches Hallo an alle. Dieses Mal Seminar-Spezialausgabe. Wir haben den Young Snow Professional Award, der auch eben Charly-Sam Award jetzt heißt, in Anlehnung an unsere ersten Unterstützer der ersten Stunde, die leider beide viel zu früh verstorben sind. Und haben hierzu eingeladen, dass uns also junge Professionisten, sowohl Praktiker wie auch Wissenschaftler aus dem Bereich Schnee und Lawinen, ihre interessanten Beiträge zukommen lassen und wir dann 3 dieser Einträge prämieren und auf 3 Konferenzen schicken. Zum einen auf die ISSW in Amerika, dann das Lawinensymposium in Graz und die Disaster Risk Reduction Konferenz, glaube ich, heißt sie, in Innsbruck. Heute sind die 5 besten Vorträge noch da, live in Präsenz. Wir haben leider ein bisschen schon Probleme gehabt mit der Technik. Das funktioniert nicht ganz so gut, wie wir uns das vorgestellt haben mit den verschiedenen Bildschirmen. Hoffentlich funktioniert es bei den Vorträgen jetzt besser. Ich werde jetzt gar nicht groß noch irgendwas erklären, außer wie wir unser Rating machen. Und zwar, ihr seht es im YouTube und auch im Zoom in den Kommentaren unten einen Link, den könnt ihr anklicken. Oder mit diesem QR-Code einfach mit dem Smartphone abfotografieren und dann kommt ihr auf eine Plattform, wo ihr mit raten könnt und einfach die 5 Vorträge, die jetzt vorgestellt werden, bewerten könnt. Zum einen inhaltlich, wie gefällt euch das, zum anderen auch, wie ist die Präsentation. Die 5 Vorträge werden in Englisch gehalten, weil auch die Konferenzen zumindest, also der Hauptpreis, die ISSW auf Englisch sein wird. Fragen aber sehr, sehr gerne auch auf Deutsch. Wir werden das dann weiter übersetzen. Und ja, auch die ganze Abstimmung kann also ruhig auf Deutsch oder ist auch das Formular auf Deutsch. Gut, und dann starten wir gleich hoffentlich mit dem ersten. Michi Binder wird uns was vorstellen über Snowpack und wie man die Initialisierung von Snowpack machen kann mit Schneeprofilen, die man im Gelände aufgenommen hat. Jetzt schauen wir, ob das auch von der Technik her funktioniert. Das sollte hoffentlich ein bisschen warten jetzt. Okay. Ja, da den schon. Jetzt müssen wir
ja, das sind dabei. Das ist nur dieses Ding. Ja.
Achso, vom Restaurant auf Präsentationsmodus.
Ja, das ist hier oben.
Okay. The stage is yours.
Ja, ich muss noch an den ersten Slide. Das ist auch so langsam.
Ich glaube, das ist eine Präsentationsmodus. Stecke mal den aus.
Das ist nur das.
Ja, dann schauen wir, ob er das lieber macht. Den tragen wir mit. Immer noch nicht auf der First Slide, aber.
Also hier auf dem Laptop ist es jetzt, aber hier nicht. Dann lassen wir können selbst mal probieren mit dem, oder?
Mhm.
Da ist es halt. Ist es bei dir offen? Ist es nur das gemacht oder siehst du es bei dir zumindest schon? Ja,
Ja, ich sehe es gleich.
Siehst du das Gleiche? Das? Ja, aber es dauert alles lang.
Das hängt da generell. Ja, ist jetzt aber, bis wir das einrichten haben. Tut uns wahnsinnig leid.
Ich habe meine mal drauf und die anderen können wir alle über den Stick sprechen. Bist du in dem Seminar dazu?
Okay, next try.
Okay, versuchst du gerade zu teilen wieder?
Ja, das sollte jetzt gehen. Das sehen wir noch nicht. Bei mir hätte es.
Ich kann mal probieren, ob es dann halt hier auch schneller geht. Und dann durchklicken. Dann müsstest du halt kurz wieder rausgehen.
Ich steige gerade aus, aber es dauert. Einen versuchen wir, ansonsten lassen wir es nur, also ohne online machen und halt auch in Präsenz. Dann darf es nur ihr mitraten. Oder halt die anderen noch mit Video aufnehmen. Aber wenn mein Laptop.
Paul, ist es dein Rechner, sondern ein anderer Rechner?
Nein, wir probieren an mich sagen.
Okay.
Weil, kannst du ihn raushauen? Bei mir zeigt es noch an, dass du Paul kannst.
Ja, aber meinst du zu wieder auf?
Ja, denkst du mir? Kann man nicht teilen, weil es immer das.
Ja.
Aber jetzt kann ich aber.
Jetzt soll ich meine Adresse.
Ja. Ja,
Genau.
Schauen ist gut. Ist schön.
Also da eine, dass es geht, weil der Krux ist drinnen.
Ja. Nein, jetzt soll es gehen.
läuft.
Es reagiert auch relativ gut aufs Klicken. Ja, also kann jemand sagen, ob die online nicht hören können? Was ist eigentlich?
Okay. 7 minutes.
Right, thank you very much. So I'm going to talk to you today about my project. I've been working on with the avalanche warning service Tyrol over the past year. And during this talk, you'll learn about a new model chain that actually connects snow cover observations, so snow profiles, with snow cover models that simulate the snow cover over a period of time. And this model chain actually runs, already runs operational at the Avalanche Warning Service Teil now for a few weeks. And yeah, let's get started. At the beginning, to get everybody on board, I want to show you a few plots that you will see a little bit more throughout this talk and other talks later. And I want to start with a snow profile here obtained by Patrick Nahles a few weeks ago, actually here in the AXA Meditation. And I guess most of you know how a snow profile looks. We see the hardness profile, temperature profile, and also the grain types here on the right side. Clear for now. Now let's simplify this plot and color code the grain types as shown here. So now we still see a hardness profile and temperature profile, but the grain types written down on the right side before are now color coded here. Why do we need this? Well, the output of snow cover models is always the snow cover over a period of time. So in this plot here, we now have the x-axis showing the time, the vertical, the y-axis is still the height of the snowpack. Now we don't see the hardness or the temperature profile anymore, but we do see, we still get a feeling of the snow cover evolution because we can see snow accumulation, we can see the settling of the snowpack, and we can even see the transformation of new snow particles to like facets or rounded grains, for example. We'll get back to that plot in a few minutes, but let's get to the snow cover models and model chains. So traditionally and up to today, avalanche warning services only use snow cover simulations based on the data from automatic weather stations, as I see here. They sometimes couple it with numeric weather prediction models to also get a short forecast. And then the output is as shown here on the right side. So we see the snowpack evolution plot here, but now it's showing the snowpack evolution for the whole season. At weather stations, we always have to simulate the whole season because we can't see into the snow. And this is what we see here. The snow builds up over the whole winter season. Then we have also the melting in the end in the spring season. So there are two disadvantages of these simulations. We are always tied to the locations of the weather stations. And what happens, for example, if the simulation that misses a feature, like for example, rain crust or the formation of surface hoar at a certain point in time during this during the season? Well, then the simulation for the remaining season loses it's not representative anymore, you can say. Maybe this might be worse or better, but it can happen that the rest of the season in that case is not really useful for the avalanche forecast anymore. To tackle this problem, we now wanted to start simulations at some point during the season. And to do that, we combined snow cover simulations with observed snow profiles, as you also sometimes observe it or obtain it in the field. So now we initialize the snow cover simulation with a snow profile we observe, couple it to weather prediction data. And now, as you can see in the snowpack evolution here to the right, we already start with a snowpack in the middle of the winter season and simulate the snow cover evolution from that point onwards. And the benefit now is we know that the old snowpack, as you can say here in the beginning of our simulations, is really, really good and correct because it's based on our observations from the field. So a few words on the model chain itself. So we initialized our simulations with snow profiles. What do we need for that? We need these list of parameters here for the simulation, the grain type, grain size, and so on. And from normal snow profiles, we get the 4 of these here. But we usually, and that's definitely required for the simulations, we are usually missing the density. Snow profiles give us the hand hardness. And so the first step of that model chain was to use the parameterization of Fabiano-Monti to then parameterize the density based on hand hardness and the other properties of the different layers of the snowpack. with that, we can start or initialize our simulations. We then use the weather prediction data for that location of the snow profile. Therefore, we need this list of parameters here, but I won't go into details here due to time constraints. And then we can run or drive the snowpack simulation based on the model data. So what do we get in the end? We again see our snowpack simulation here based on the profile from Patrick. And yeah, so Patrick observed the profile almost 3 weeks ago now, here at the beginning of that simulation. But based on this model chain, now he's able to look at the snow profile. Here, this vertical line here shows actually yesterday. And this also shows the snow profile here on the right side. So you can use that tool to actually get a view on the snow profile from today, and even look a little bit into the future based on the lead time of the forecast on the weather prediction model. If luckily, or since this is now based on normal model data, we can also couple the snow cover output to many other tools that are already out there that give us a hint on the stability of the snowpack. There's, for example, the RTA from Fabiano Monti, or a model from Stephanie Meyer that can define the snowpack stability based on the snow cover simulations. We will actually learn in a later talk by Martin that we can also derive avalanche problems by the simulations, and we can also derive danger levels. Short take-home message: we have developed a model chain that combines snow cover observations with snow cover models, and it already runs operational today. And it also has the potential to add a lot more. It has the possibility to add a lot of extensions to it. And with that, I want to conclude and show you that all the tools we are using are all available online, and maybe other avalanche warning services also want to use them at some point. Thank you very much.
Any questions from the audience or online? Michi. Martin is checking.
Michi, I have a question already.
Yes.
You've shown it for one specific snow profile in one certain location.
Yeah.
Can you comment on how it works with the spatial variability or like topography features and how this is entering the model chain, or like, so pretty much talk a lot about time now. What about space? Yeah,
about space. So definitely it's still only we only use a point observation in the snow profile, and in that case we also we obtain the exposition and also the slope angle, for example, of the snow profile, where we observe it, and then we run the simulation for this specific location. So if you want to extend it in a spatial domain, we definitely have to either obtain more snow profile that we can get an average for a certain area. But yeah, this model chain so far is only for individual, let's say, snow profiles and then point simulations. Yeah.
Gut. Online? Nothing? Sehr gut. Dann vielen Dank für das Lösen des technischen Problems. Wir dürfen auf deinem Laptop bleiben. Auf dem Stick sollten die anderen sein. Wunderbar. Genau. Christoph Hesselbach wird uns den nächsten Vortrag geben. Und da geht es jetzt darum, wie man automatisch Lawinenklassifikationen machen kann. Und ich mag da gar nicht viel deiner Zeit raus. Du wirst uns erklären, was du genau gemacht hast.
Yeah, hello everybody. Also from my side, it's an honor to be here. I'm Christoph Hesselbach, and I'm talking about the elaboration and adaptation of an automated avalanche terrain classification in Austria. So my primary object is setting up the model chain, of course, and then do a sensitivity analysis of the model chain and defining the best input parameters for the model chain. I'm working in a study area which is about 600 square kilometers wide and covers high alpine terrain. So, but before I get to the model chain, it's good to get some fundamentals first. So when we're talking about avalanches, it always is important to get the sizes as well. So the named organization classified the avalanches into five categories, ranging from small to extreme large. And on the picture, you see a classical size 3 avalanches and some 2s on the side. And when you're out as a professional or as a recreational in the backcountry, those are the sizes you worry the most about, and that's the focus of my work. So another basic classification comes from Canada. It's the avalanche terrain exposure scale, which basically divides the terrain into 3 classes. We have the simple terrain for low angle terrain with limited exposure. We have the challenging terrain with some runouts. And we have the complex terrain, which is marked in red for high exposure due to avalanches and other hazards. In the past recent years, there have been some various publication on terrain classifications, but I won't go into detail with that. I just want to tell you that we are building the model chain partly on some open source algorithms. And the first goal, the main goal for the work is that to work fully open source, to do this for Austria, and to include the avalanche propagation itself in the map. So the approach, how to get there. We have a classification process and the validation process. In the classification process, I'm looking at the avalanche mobility and combine this with the artist classification. In the validation process, I have like 3 objects. First of all, the validation with the size classification, some real avalanche data, and of course, an expert assessment. The model chain itself builds up on 3 steps. The first step is the potential release area delineation, and which is based on 4 parameters: forestation, slope, roughness, and wind shelter index. The wind shelter index is something to cover the curvature of the terrain. And the output of the delineation is categorized into 5 categories based on their size, which is important for the next step. The next step is the avalanche mobility. And the avalanche mobility, I'm using the FlowPy model, which is a data-based empirical model. And it's basically based on 2 principles: the routing, which is the path identification, and the stopping criteria. And here comes the categorization from before, because every single size of potential release area becomes a different stopping criteria. In the third step, I combine this with the artist classifier and merge all together to get the final 3 classes. Here's an example for how spatial map view. First, we have the terrain factors, which are primarily forests and steep slopes. In blue down there, you see the potential release area in that area. And on the second, you see the results of the avalanche mobility, which is the travel length and the impact pressure. On the side, you see a final map, which is still in raw, but this is how it's going to look like. And this is pretty much like the picture at the beginning. We have some different areas marked as in red, blue, and green. Okay. No. Okay. Is it working? Oh, okay. Well, but I mean, I continue. The screen is like blocking my. Oh, no. Okay. So, but how to validate the results? So first, I have a qualitative validation and a quantitative validation. For the qualitative validation, I back calculated a set of 19 avalanches from the LVD Tirol. And on the example, you see a picture which is not fitting pretty good. But on this slide, we get a much better result. And to sum this up and to know where to start, I plotted the alpha angle, and for like a size 3 avalanches, I ended up like having like a 30-degree angle. So in the plots, I summed the results up, and you can see the red dotted line is like the range of a size 3 avalanche, and for the travel lengths we are already quite good in the range, but for the impact pressure we doesn't, and this raises the question why. And the impact pressure, it's hard to measure. I just took the maximum right now out of my simulations, but the impact pressure comes from after event perspective. So I have to look, so where exactly to pick out the value from. And this brings me to my next point. The quantitative validation, it is still in progress because I'm working it right now. And for this, there is this path identification quite necessary. Because with this, it is possible to look at every single potential avalanche in the study area, and then I can get out of the value and to plot this with the ranges of the classification schemes from the European Avalanche Warning Service and the Canadian Avalanche Association. And this brings me to my next steps. The next steps is, first of all, I still have to optimize the potential release area delineation, because right now we have about 40,000 avalanches in my potential avalanches in my study area, and so I need to manipulate the code for the path identification, and of course the expert assessment at the end, who's looking at our final maps. And yeah, as an outlook, I want to create a tool for safe travel in avalanche terrain for all of us. Thank you very much.
Fragen, any questions, online or from the audience?
Ja, ich habe das jetzt nicht ganz mitgekriegt. Was war mit dem Alpha-Winkel mit 30 Grad?
Das ist ein statistisch basiertes Modell, und da sind quasi das Stopping Criteria ist der Alpha-Angle, wo man quasi sagt, okay, wir haben aus der statistischen Analyse von so und so vielen Lawinen, können wir sagen, dass der Alpha-Angle ungefähr 30 Grad bei Lawinengröße 3 trifft. Und so, es ist ein Unterschied, ob man jetzt prozessbasierte oder physikalisch basierte Modelle hernimmt oder statistisch basierte Modelle. Und die statistisch motivierten Modelle, die haben eben quasi nur diesen Alpha-Angle als Stopping-Kriteria, die man eben kennt aus observierten Lawinen.
Das heißt, ich kann davon ausgehen, dass der Alpha-Winkel nicht kleiner wird wie 30 Grad.
Bei der Größe 3, also wenn wir jetzt zum Beispiel Katastrophenlawinen anschauen, also das Modell wurde ursprünglich in Norwegen entwickelt, und die haben also bei Größe 5 und 4 sprechen wir von einem Alpha-Winkel um ungefähr 20, wenn nicht sogar 18, also das geht dann viel weiter raus. Also umso kleiner die Lawine, umso geringer der Auslauf. Also zum Beispiel in der EAWS-Tabelle heißt es bei Größe 3, die Größe 3 stoppt ungefähr bei dem 30 Grad Geländepunkt und geht noch ein bisschen weiter. Und Größe 4 und 5 gehen bis runter ins Tal. Das heißt, da ist der Alpha-Winkel viel flacher. Genau.
Super,
Danke.
vielen Dank. Super in der Zeit. Frage? Top. Dann ist gerade Sommer.
Das
Mit
wird
unserer
Sommer.
Hanna. Ja, dann kommen wir gleich zum nächsten Vortrag. Hanna Rohringer wird uns ein bisschen was erzählen, wie man in modellierten und auch beobachteten Schneeprofilen eben verschiedene Krusten oder kantige Kristalle in Krusten da tracken kann und wie sich das vorkommt. Rest lasse ich dich erzählen.
So let's start. I want to thank you first for the interest from the results of my master thesis, which I wrote supervised from Christoph and Rainer Prinz. And together we tried an approach to how to compare and track facets around crusts in observed and model snow profiles. So let's just drop into it. And dry snow slab avalanches are often associated with facets around crusts. And especially in the Tyrolean Alps, this kind of weak layer is often associated with a dry wet faceting process. And the team of the Avalanche Warning Service Tyrol has luckily one player who is really good in assigning the development phases of this kind of specific weak layer and derive a spatial pattern of it. And in this figure, you can see the result of it, where the pink pins are indicating the development phase of the respective weak layer, and the red line gives you a kind of overview of how often the respective weak layer has been triggered and contribute to avalanche release. And all the information you can see in this figure is based on a qualitative human decision. So we asked ourselves if it is possible to reproduce this figure with a machine-based method, and therefore we need to access the development period of the weak layers. And for that, we followed the approach of Rohringer Hanna from the snow profile alignment and similarity assessment. But what do I actually mean with snow profile alignment and similarity assessment? In order to access the similarity, it needs to define a similarity measure, and Rohringer Hanna introduced a distance function based on structural difference from the snow grain height and the layer hardness. And with this information, the algorithm computes for every possible sequence of layers the distance value, stores it into the local coast matrix, and then aligns the best matching layer to each other. And after that, we are able to compute similarity values for the 4 major grain types, which are new snow crystal weak layers, crusts, and bulk layers. And with the information based on the similarity assessment of the weak layers and crusts, which consists of decor, surface hair, and faceted crystals, we asked ourselves if we are able to derive a signature for weak layers that originates from dry-wet faceting. And in order to do that, we looked at observed profiles and a combination of observed and simulated profile. And to keep in mind, the signature is derived from a statistical evolution of the similarity values from the selected profiles. Here you can see the statistical distribution, where one means that the profiles are completely dissimilar, and one means that they're similar. And with this information, looking on the right-hand side of the slide, you can see that with this approach, it is not possible to, Okay, sorry for the interruption. With this approach, we are not able to derive a signature for the combination of observed and simulated profiles. But having a look at the values of the observed snow profiles, you can see that the values are looking kind of reasonable. And with this information, I want to go into the hierarchical clustering, which you can see in this figure. The hierarchical clustering groups profile with high similarity values together into one group. And that the group is changing, you can see on the color chains in the top of the bottom. Below of it, you can see the stratification of each snow profile in the cluster. And on the bottom of the slide, you can see the distance distribution of each cluster. And actually, our initial idea was to use the cluster information to reproduce the figure from above. But having a deeper look into the snow profiles from the cluster, we concluded that often the profiles come from a different genesis process. So with this approach, we're not able to reproduce the figure, but we are able to conclude other information from the cluster and from our derived signature. And now I want to show you some examples. This is an example of cluster 13, where you can see that the same snowpack stratification can be found in 4 different microregions. It can be found in the northern aspect in a very narrow elevation band, and all these snow profiles have been digged within a time period of 2 weeks. And this is an example of cluster 3, and also this figure can give a forecaster a hint that there might be a critical situation, because in the southern aspect you can find the sequence from crusts followed by faceted crystals followed by crusts, also again in a very narrow elevation band, and mostly of these profiles have been dug in within 1 month. But we have also to say that for some other clusters it's harder to draw a conclusion, because everything is kind of diverging. And to sum it all up, this was my first attempt to derive a signature for the dry wet faceting. And with this approach, it's not possible to detect the development phases, but we can gain other information from the resulting clusters. So we can support the forecaster by finding similarities in a large quantity of observed snow profiles and point out potential dry wet faceting by suggesting possible regions, elevation, and aspects. So in other words, if there is a significant cluster, we can give the hint, we can give the forecaster a hint to look deeper into the region, elevation, or in the aspect. And yes, thank you for your attention, and I'm looking forward to your questions.
Danke. Fragen?
Bei dieser Clusterung die Exposition und die Höhenlage auch mit einberechnet? Das nicht so?
Nein, das geht nur aufgrund eben der Ähnlichkeiten von den einzelnen Schichten im Schneeprofil. Also das, was man gesehen hat vorher in der Abbildung, die Elevation und der Aspect, das ist das, was man dann aus dem Schneeprofil des Clusterwordens ausgeholt hat.
Aber ich kann nicht verhindern, dass er einen Südhang mit einem Nordhang vergleicht in einem anderen Gebiet.
So kann ich es nicht verhindern. Grundsätzlich könnte man es verhindern, indem ich es ja nicht erlaubt. Also indem ich in diesem Datensatz, mit dem ich Cluster einfach nur Nordprofile reingehe. Aber ansonsten nimmt er alles, was er kriegt, und geht nur auf die Similarity Values von den Weak Layers und den Kosten. Von Quantitäten und Kosten.
Online-Fragen? Noch einmal
man kennt ja mittlerweile von typischen Schneeprofilen, die werden ja auch insofern geclustert, dass man sagt, Hard Slab, Soft Slab, wo befindet sich was in der Schneedecke, hat es auch das, was damit zu tun, da steht so eine allgemeine Kategorisierung von einem Schneeprofil machen kannst. Verstehst du das hin?
Mit meinem Ansatz ist so, wie man das jetzt angeschaut hat, glaube ich, nicht wirklich. Also ich schaue mir wirklich nur die Abfolge von Krusten und kann das teilen und das Recht darüber.
Okay. Also es bezieht sich nur auf Schwachschichten, nicht auf die Qualität vom Schneebrett selber.
Ja.
Sehr gut. Vielen Dank. Noch einmal der Aufruf in die Runde und auch online, bitte kräftig mitvoten. Ihr könnt einzelne Vorträge nur bewerten oder auch alle nachher gemeinsam. Würde uns einfach bringen, damit das Ganze wirklich objektiv abläuft und wir möglichst ein breites Spektrum haben an Rückmeldungen. Gut, then next one on the stage. Oskar Dick wird uns jetzt ein bisschen etwas erzählen, was es uns bringt, wenn wir in Lawinenexperimenten Partikel ihre Bahn mittracken und wie uns das helfen kann, Lawinensimulationsmodelle zu verbessern. It's not, it's here. Perfect.
So hello everyone, my name is Oscar. I'm currently doing an internship at the BRP, and today I will present how we use particle tracking in field experiments in order to improve our avalanche simulations. So first, how can we track snow particles? So the BRP has been conducting field experiments in the Nordketten ski resorts for 2 years now, using what we call avanodes in order to have an insight on the inflow dynamic of the snow particle level. And you can see a picture of the avanodes in the upper right corner of the left panel, and they consist in sensors placed in a protective capsule. And we place these avanodes in the release area of the Stellt that you can see on the left picture. And once the avalanche is released, they move with the avalanche flow, and we can extract in real time the position as well as the velocity or acceleration. On the other hand, the open source avalanche simulation framework, AvaFrame, can be used to simulate avalanche flows in a given topography. And if we use the Stellt topography, we can simulate the avalanche flows we observe during the field experiments. And we can also extract the flow quantities at a particle level, so we can compare the simulation results with the experimental results. So a long-term issue in the avalanche flow modeling is the expression of the friction of the avalanche flow at the basal layer. So since the beginning of the avalanche research in the early 20th century, many different friction models have been tested. And in AvaFrame right now, 3 of them are implemented, and the user can choose to use one of them. And there is the molecular model, which corresponds to a dry friction, for example, between 2 solids. There is a Fermi model, which adds like a turbulent friction to this dry friction, and the samosate, which also adds like a flow thickness dependency to the friction expression. However, when we compare the simulation with the experiments for each one of these friction models, the comparison was really not satisfying. So we decided to adapt the friction model, which ended up in the expression you can see here, in which the basal shear stress tau B now depends on 3 parameters, which can be calibrated, which are the dry morpholon friction coefficient mu, we can see here, the turbulent friction coefficient Xi here, and the minimum shear stress tau 0. Yeah. So in order to calibrate our model, we decided to compare simulations with experiments. So as you can see on the left figure, we compared the velocity envelope obtained for the simulated flow using this adapted friction model and different values of the parameters we want to calibrate. And we compared this velocity envelope to the velocity of 3 avanodes recording during an experiment in February 2022. And as you can see, depending on the values of these parameters, the comparison is more or less satisfying. And in order to have a closer look, we decided to compare the mean velocity of the simulated flow with the average velocity of the 3 nodes. And it gave us the box plot, as you can see on the right figure, in which we can see that the minimum difference is obtained for this set of parameters, which are mean being equal to 0.6, tau 0 being equal to 70 Pascal, and Xi being equal to 4,000 liters per square second. It must be noted that the avalanches observed in the Stellt are small, and therefore this corresponds to our adapted friction model calibrated for small avalanches. So now the previous approach was at the whole avalanche scale, and we can do the same approach but at the particle level. So we picked the numeric particles which are in the vicinity of the avanode in the release area, and we decided to compare their behavior to the nodes both in the spatial and temporal domain. So on the left figure, you can see the trajectories of these numeric particles as well as the trajectories of the 3 nodes. And on the right figure, you can see the velocity of evolution of the nodes as well as the velocity evolution of the numeric particles. And as you can see, for 2 nodes out of 3, the velocity matching is very satisfying, with only 1 node, which corresponds to the red line, which has a maximum velocity which is way slower than the other one. And regarding the trajectories, they also have very similar trajectories, despite the numeric particles going a little bit farther down along the Stellt range. So now we have calibrated our friction model using both the spatial and the temporal approach, both at the whole avalanche scale and at the particle level. And now it would be interesting to combine both the spatial and temporal information to make the comparison between experiments and simulations easier. And to do so, we decided to make a change of coordinate system and to transform the flow quantities in the Teil coordinate system. And what we call Teil is the avalanche path automatically generated by extracting the avalanche center of mass at each time step. So basically the Teil coordinate system is a coordinate system which follows the avalanche path. And now, so after transforming the flow quantities in this new coordinate system, we decided to plot the velocity evolution as well as the altitude evolution of our simulation along the Teil distance S. And this gave us the plot that we can see here. And on the same plot, we also added the avalanche velocity along the Teil distance S. So as you can see, we can extract again the maximum velocity of the numeric simulation, and as well as the maximum velocity of the nodes. But this time we can also see the maximum travel length of our simulated flow, which corresponds to this distance here, as well as the travel length of the nodes. We can also spot the release area, which corresponds to this zone here on the left, as well as what is likely the deposit or runout zone, which corresponds to the right length here. And the altitude envelope provides us information on the topography evolution and how the flow reacts to it. And the envelope is expected to get thicker when the avalanche path turns and to get thinner when the avalanche path is more straightforward and goes perpendicularly to the altitude lines. So as a conclusion, we showed that the avalanche can be successfully used to calibrate a friction model. We also showed that our adaptive friction model provides simulation results which fit the experimental data in a satisfying way, both in the spatial and temporal domain. We also showed that the Teil coordinate system combines the spatial and temporal information, provides a spatial reference to define the travel length and altitude, and allows to put the sensors as well as the numeric particles in spatial relation to the whole avalanche flow. And eventually, we successfully tested the track of numeric particles in simulation. And the next step would be to see how a change in the avalanche physical properties will affect the trajectories of particles in order to go towards trajectory prediction regarding possible debris or avalanche victims. Thank you.
Thank you. Fragen? Online, nichts, glaube ich, ja? Yes. Yeah. Thank you very much. And then we come to the last one. So, der Martin Perfler wird uns jetzt zum Abschluss noch erzählen, wie wir Lawinenvorhersagen verbessern können, indem wir Lawinenprobleme aus verschiedenen Modellketten herausziehen können, automatisiert. So im Groben zusammengefasst. Details von Martin selber. 7 Minuten, Martin.
First of all, thanks to the talks before, they were quite interesting, and I'm now happy to show you some research we gained within the last winter season about assessing avalanche problems for operational avalanche forecasting based on different model chains. Snowpack model exists for more than 20 years now, but only recently they are used in avalanche warning services. Under operational constraints, a snowpack model can be driven by automatic weather stations, numerical weather predictions, initialized by observed profiles, or a combination of all of them, with the goal to get an information about the layering within the snowpack and its evolution. But now, forecasters are confronted with an overwhelming amount of information and either don't have the time or the knowledge to interpret all of them. Therefore, there's this great need of a better accessibility of this immense data treasure. But help is on the way. For example, from Christina Perez and her colleagues, where she's automatically assigning danger levels based on snowpack simulations and machine learning algorithms. or from Flo Höller, giving us this game changer and the possibility to average thousands of profiles to one single one. There's also the work from Ben Reuter, where he's tackling avalanche problems and their climatology. His idea catched us because he's tackling avalanche problems, and they are building the entry point of the avalanche hazard communication within the avalanche polytech. So we ask ourselves if he can set up a model chain and adapt his algorithm to predict avalanche problems. At first, we initialized snowpack with automatic weather stations. Then we applied our algorithm to get a first objective guess of the prevailing avalanche problem. And furthermore, thanks to the big effort of Michi Binder, we were able to initialize snowpack with observed profiles and only drive them with numerical weather predictions to again apply our algorithm to get an avalanche problem. The European Avalanche Warning Services agreed 5 years ago on 5 different avalanche problems. Today, we are only going to focus on 3 of them: new snow, persistent weak layer, and wet snow. The main concept of the algorithm can be broken down to a few major decision points. At first, it identifies and tracks potential weak layers. Then it verifies if there is a coherent slab above the weak layer supporting correct propagation and initiation. Then it calculates stability criteria. And if certain thresholds are met, it assigns an avalanche problem. Now I'm going to show you a small data example from the last winter season from our test site in the Axel-Munitzum, where we have a well-equipped weather station as well as a nice area for field observations. Here you can see the evolution of the danger level from the past winter season in the colorful dots, going from low danger level 1 to high danger level 4. In the gray shaded bars are reported avalanche accidents where people were involved. Overall, it was quite an average winter season with 2 critical phases. And especially the second one in the beginning of February was unfortunately with a lot of avalanche accidents. So now let's see what avalanche problems were assigned by the model and compare it to the assessment done by the forecaster. So for new snow, persistent weak layer, and wet snow, for each of them in the upper part will bars pop up if a problem is assigned. And in the lower part, we will compare it to the assessment by the forecaster. Month of coding, and we gained this plot. But you know what? We were pretty happy with it, because avalanche problems based on simulations show a fairly similar behavior than a forecaster. It assigns problems in similar periods than a forecaster. Of course, looking more into detail, one can see a difference in the onset and the offset of the problem. So for that, let's jump into the detail, and we will analyze this critical situation in the beginning of February for the persistent weak layer problem. So we can run the simulations for different aspects, in the upper part for the northern aspect, in the lower part for the southern aspect. And as we remember, the algorithm identifies and tracks potential weak layers. It verifies if there's a coherent slab. It calculates stability criteria and then assigns a problem. We were again quite encouraged by this plot because we already can see a great potential of this algorithm, because it can give a forecaster a first objective guess when a problem will be critical. And furthermore, it can help him in his decision-making in which aspects are they relevant for how long, as it is not that long persistent in the southern aspect than in the northern aspect. Now let's compare it to the assignment by the forecaster. And here we can see, again, this great potential of helping a forecaster, because the model detected the persistent weak layer problem a few days earlier than the forecasters. It might have given a hint to look into more snowpack simulations or profiles or observations to decide if it's critical or not. And furthermore, forecasters tend to keep the persistent weak layer problem longer than it might be necessary, so it can give him a hint. So, summing it all up, we're pretty happy to say that avalanche problems based on simulations show a fairly similar behavior in the forecaster. The algorithm can support the forecaster with a first objective guess, with a better timing, and in assessing the prevailing aspects. Looking into the future, we plan to extend the snowpack stations within the regio with the algorithm. We want to apply our new model chain to observe profiles, and we want to tackle more avalanche problems. Our algorithm is part of our awesome project. It's open source, feel free to join us. Thank you.
Auch perfekt in der Zeit. Dazu Fragen noch. Du bist da online im Chat, hat sie auch nichts getan. Genau, nochmal die kann man nochmal auf, dass wir den Code nochmal sehen. Vielen Dank. Du hast eine Frage.
Ein kleiner Frage muss ich fragen. Martin, kannst du, ihr habt jetzt die 3 Lawinenprobleme ausgesucht. Warum die 3? Warum nicht die anderen? Was ist die Schwierigkeit an der Geschichte mit den verschiedenen Lawinenproblemen? Und direkt da dran, vielleicht Frage 2, hat inwiefern Lawinenprobleme dann auch gefahrenstufenmäßig? Also kannst du warum die, warum nicht andere? Was macht das mit dem Modell aus? Und hängt das auch irgendwie, hängen gewisse Lawinenprobleme irgendwie an den Gefahrenstufen dran?
Warum die 3? Weil wir die momentan bewältigen können. Wir hätten den Algorithmus schon darauf angewendet, dass wir Triebschnee vorhersagen können. Es scheitert momentan am Snowpack-Modell selber, wie Triebschnee quasi dargestellt wird, von wo nach wo wird der Triebschnee verfrachtet. Da haben wir einfach mit dem Output vom Snowpack momentan Probleme. Aber prinzipiell sollten wir es schon können. Und
aber was unterscheidet die dann modellmäßig von den anderen? Warum ist das bei den einen schwerer als bei den anderen?
Jetzt zum Beispiel beim Wet Snow Problem haben wir einen klaren Anhaltspunkt vom Snowpack Model schon gut implementiert, wo wir sehen, wie ist der Anstieg vom Wassergehalt in der Schneedecke. Das haben wir super da. Persistent Weak Layer. Identifizieren wir kantige Kristalle, die was sich auf der Schneeoberfläche bilden und können die verfolgen. Das kann man gut erfassen. Und bei Triebschnee sehen wir es einfach nicht. Und für Gleitschnee ist es allgemein ziemlich komplex und eigentlich nicht vorherzusagen. Deswegen haben wir es keine Gefahrenstufe selber können wir in dem Approach nicht darstellen, weil eine Gefahrenstufe ist ja immer zusammen mit der Verteilung von dem Problem über einen größeren Raum. Und das, was wir momentan drauf haben, ist jetzt quasi für eine Station oder ein Profil, wie der Michi gesagt hat, das zu simulieren und für diesen Punkt momentan Vorhersage zu treffen.
Super. Vielen Dank. Vielen Dank den Vortragenden für die interessanten Vorträge und auch, dass Sie die Zeit eingehalten haben. Trotz der technischen Probleme sind wir rechtzeitig fertig am Ende. Vielen Dank euch für die Aufmerksamkeit, auch online, und vielen Dank für das Mitvoten. Wir waren dieses Jahr, wie ihr gemerkt habt, sehr wissenschaftlich unterwegs, soll aber nicht nur sein. Also es können genauso auch Beiträge aus der Praxis sein, die auf diesen 3 Konferenzen sehr, sehr wohl auch gefragt sind und die wir gerne hinschicken würden. Also auch da für nächstes Jahr gerne auch an die Praktiker. Es ist genauso interessant, was ihr draußen im Feld erfragt, erforscht, für die Community und nicht nur das, was am Computer gemacht wird. Danke, Harry, dass du uns den Rahmen hier ermöglicht hast, dass wir das da machen haben dürfen. Ich hoffe, es war für euch auch was Interessantes dabei. Vielen Dank auch für das ganze Organisieren, Martin, und Matthias, der ist im Feld unterwegs. Und ja, wünsche euch einen schönen Nachmittag und dem Lawinenkommissionskurs da jetzt Mahlzeit und schöne 2,5 Tage dann noch am Kurs und hoffentlich sehr lehrreicher. Und wenn ihr Fragen habt, die meisten Kontakte gibt es sicher zu den Vorträgen auch beim Christoph oder beim JD. Die können euch sicher auch direkt in Kontakt bringen mit dem Vortrag. Gut, Präsident, Vizepräsident, habe ich was vergessen? Ja. Dann vielen Dank und einen schönen Nachmittag noch.
Danke. Okay. Geht schon? Ja, vielen Dank euch. War eine interessante Präsentation. Ich habe natürlich inhaltlich einiges schon gekannt, weil ja Teile von euch ja bei uns auch waren und ich schon mitgekriegt habe, dass sie länger dran ganz interessant waren, aber Pascal und von dir die Sachen, die ich nicht so wisst, das mit dem Klassifizieren von Gelände finde ich